Swayam Prabha. Digital India. Educated India.
Let us complete the discussion on kinetic theory of gases in this lecture. In this lecture, we will discuss about sphere of influence, particle collision frequency, mean free path, equilibrium velocity distribution, which is often referred to as the famous Maxwellian distribution, speed distribution function, and different particle speed definitions. In the previous lecture, you may recall having seen this sketch where we tried to explain the radius of influence of a molecule or an atom when it is colliding with another, and we said that effectively this gives a picture of a set of billiard balls interacting with each other, colliding with each other. So, it is often referred to as the billiard ball model. Then we said that there are two ways of picturizing the particle motion. One is the actual path that is followed by the particle during collisions, where it may be following its path with a constant speed. Essentially, the mod of the c vector remains constant, but it keeps changing its course because in course of its movement it keeps interacting with other particles, colliding with them, and each collision would change its course. It may also be colliding with container walls and things like that. Therefore, the actual path is quite complicated. To idealize it, often a hypothetical or imaginary path is proposed, where the particle is seen to be moving with a constant c vector in terms of direction as well as magnitude. There is no interruption, there is no modification. So, these are different ways of modeling the particle movement. The radius of influence of the particle, which may be a molecule or an atom, sweeps out a cylindrical volume per unit time. This is something that we have to kind of picturize, and the picturization comes simply from a figure like this. Here it gives you the idea of the sweeping that we are talking about. And when we talk about the sweeping, it is basically the pi d square, the d being the radius minded, not to be confused with diameter, and that area is actually sweeping a volume essentially per unit time, because the particle is moving with its average velocity c bar, and this is easier to figure out with the imaginary straight path figure that we talked about. Now, if the number of particles per unit volume is n, which is basically the number density, then as the particle moves along, the particle would encounter n times pi d square c bar collisions per second. This number is called as single particle collision frequency. So, what we mean to say is that though we are considering that the particle does not get deviated from its path due to collisions, we assume a hypothetical straight line movement of the particle and so on, but going by the number density, we would say that in the region, in the volume that the particle sweeps per unit time, anyway it is going to come across n number of particles, where n into pi d square c bar number of collisions per second are going to happen. It is not n number of particles really. What I meant to say was, at the rate of n number of particles per unit volume, it is going to encounter particle collisions. That is a more precise way of defining it. So, this gives rise to the definition of so called single particle collision frequency. it is denoted by z dash, and that is given by n pi d square c bar. Now, this pi d square is often called as the collision cross section, and it is indicated by sigma. Coming to the mean free path, it is the mean distance traveled by a particle in between collisions, and it is denoted by lambda. Lambda is given by c bar by the z dash that we just defined, and if you just plug in the expressions, you will get 1 by n pi d square. Now, this result is based on a simplified model where the moving particle encounters other particles which just lie on its path as though they are fixed in their respective locations. We do not consider that the other particles are also moving around with their own velocities. If they were, and in reality they do, that would definitely affect the collision frequency, since the relative velocity between the particles will get altered. The one which is translating at c bar and the velocity of the colliding particle both would have to be accounted, so that we ultimately come up with a formulation which accounts for relative velocity of approaching particles. So, that is a more complete, more accurate model. However, that is a more involved, more complicated model to formulate. The single particle collision frequency between a single particle of chemical species A and particles of chemical species B is given by a relation which is stated below without any proof. So, as things get more complicated, the proofs also do get complicated, and it is difficult for us to accommodate all that in a course like this, because it is introductory in nature. However, if you are seriously interested, this is one of the best books to look at for detailed proofs on all these aspects. This is an excellent book by Vincenti and Kruger on physical gas dynamics. It is a very good reference for kinetic theory, chemical thermodynamics, which is what we discussed in week 5, statistical thermodynamics and mechanics, which was dealt with in week 6, and equilibrium as well as non-equilibrium flow, which we are going to deal with in detail in the upcoming weeks, including week 7. All of these aspects are very well covered in this book to a greater detail. So, the detailing might be done by some additional reading that you can follow up with, and such proofs are directly extracted and stated here. So, we were talking about the single particle collision frequency, where two species particles are involved, one of A, the other B, and therefore, you have to bring in the presence of different species here through the subscript here for Z, and then you see that ZAB is nothing but NB, that means the number of particles per unit volume, the particle density of species B encountering particle from species A, and then the pi d AB square, essentially bringing into the influence the radii of influence of both species, and the relative velocity effect as well. CAB, it is the mean relative velocity between A and B particles where both are considered to be moving, and the C bar AB happens to be under root 8 times kT by pi m suffix AB. So, here is another term which needs to be taken account of. K, of course, is the Boltzmann constant. MAB is a reduced mass that we calculate based on particle masses of both species A and B. So, it is MA into MB by MA plus MB, where MA and MB are the masses of particles of species A and B respectively, which collide. So, having said that, the collision frequency is ultimately expressed in a form like that. Now, notice that since two different species are involved, instead of just writing D, which we were doing earlier, we are now writing D with a subscript AB, which defines the radius of influence based on combined influence of particles of both species A and B. Similarly, we see the presence of reduced mass, where a kind of weighted mass accounting for masses of both species has been introduced into the equation. For single species gas, that means you no longer have A and B, but now it's all single species. However, you are accounting for the relative velocity of the particles. If you go about computing the single particle collision frequency, then how would the expression look like? The answer to that would be an expression like this for Z, which is n by root 2 times pi d square by c bar. Notice that the moment it reduced to single species, the subscripts a b went away. That is one thing. But the second thing is, there is a presence of under root 2, which was not seen before. And we recall that the z dash expression that we had earlier, where we did not account for the relative velocity effect, we had it in the form of n pi d square c bar. So, where is this root 2 coming from? Now, where relative velocity of the particles were not considered, this root 2 did not surface. However, the moment you account for relative velocity, it would surface. However, we have to state it without any proof. Again, remember that in the two species formulation, DAB was there, now it is back to D. In the two species formulation, this was MAB, however, now it is M alone. So, there are some differences to be noted. Now, the collision counting procedure that we perform is different for single species colliding particles and multiple species colliding particles. Thus, we cannot obtain the expression for Z just by substituting MA equal to MB in the reduced mass expression that occurs in the ZAB equation. So, this is another point to be taken note of. The two equations or expressions for Z would differ by an additional factor of 2, which is basically because of the collision counting procedure, which differs between what you do for single species versus what you do for multiple species. So, such differences are definitely there. We have to just account for them in the equations that we are studying. Mean free path of a single species gas accounting for the effect of relative velocity again shows up with the factor root 2 here in the denominator. Recall that when we were looking at the lambda expression, without having taken into account the effect of relative velocity, we did not have that under root 2. There we had used the z dash expression, and we had come up with this form 1 by n pi d square. Now, an interesting thing comes up where we look at dependence of collision frequency and mean free path on pressure and temperature of the gas. So, we recall our equation of state on a particle basis, where the use of particle density as well as Boltzmann constant is there. P is equal to n kT, that is the form we are talking about. So, we now have an expression for n in terms of pressure and temperature. So, that is very interesting that through the n root you get P and T entering the expressions. So, we invoke the expressions for Z for single species, and then we try to work out the expressions as we substitute n for P by kT. Now, if you do so, this is how the expression comes up, and on simplification you will find that the pressure and temperature difference, the pressure and temperature dependence reflects in this form: P by root 2 times a set of parameters which will come out to be a constant. Therefore, Z is basically proportional to P by root T. That is the functional dependence of Z with pressure and temperature. On the other hand, if we look at lambda, this is the definition where we have accounted for relative velocity. Again, take into account this root 2, which basically indicates that we have already taken the account of relative velocity into the picture. And now if you go ahead, replace the n, you bring in the pressure and temperature here into the solution, and you can clearly show over here that lambda is proportional to T by P. Now, there are interesting conclusions that may be drawn from here. So, if you refer to those equations as equations A and B, we can infer that high temperature and low pressure, that is the kind of condition that is most relevant for most of the aerodynamic flows that we are discussing. They are characterized by low collision frequencies and high mean free paths or large mean free paths, which would mean that you have weak intermolecular forces, and therefore, you can expect perfect gas behavior from such medium. Low temperature and high pressure, if those conditions are imposed, and these are the conditions that we are already aware of, are connected with real gas effects. So, in such situations, you have high collision frequencies and low mean free paths. These are essentially recipes for strong intermolecular forces and thereby the real gas behavior. So, interesting conclusions can follow from what we have done here. Now, we come to another interesting area. We discuss about velocity and speed distribution functions. So, till now we were following a single particle and considering the collisions that it encounters with other particles, whether they were same species or different species. We had different equations to look at and interesting outcomes coming out of them, and we were looking at them as they move through the gaseous medium. Consequently, we found that expressions are available for collision frequency and mean free path based on mean velocity of translation of the particle, and it had dependence on collision cross section as well as number density. Finally, we saw the dependence of Z and lambda on temperature and pressure of the gas. Now, in a realistic situation, we have large number of particles comprising the gaseous medium. So, if we consider a system comprising of capital N number of particles, then they would have their individual instantaneous locations within that system. Let us assume the instantaneous location of one of those N particles to be given by the position vector, the vector r. This defines the coordinates of the point in the xyz space where the particle is located, and N particle locations would create a cloud of points. That can be an instantaneous picture which will change from one time instant to the other, but since the particles are usually large in number, it will follow a statistics essentially. Now, if we consider a system comprising of N particles, then they would have their individual instantaneous locations, which we already mentioned about, and the cloud of points which will follow. Similarly, the N particles have different velocities, and in the velocity space, each particle has a corresponding point which indicates the particle's velocity components. Again, all this could be instantaneous. Now, the physical space concerns the physical location of the particle, the position vectors of the different particles that we are talking about, and then you can imagine that it is more like a spherical domain within which the particles are located at different radial distances from the origin of the coordinate system. And then similarly, in velocity space, they have a typical distribution which are basically based on the velocity vectors of the respective particles. And we have drawn differential elements in both the spaces, both the physical space as well as the velocity space, because we would need that information in due course. We thereby come up with a so-called distribution function, which is a function of both those vectors that we were talking about, the position vector as well as the velocity vector, and this basically defines the number of particles per unit volume of physical space at the r vector location with velocities per unit volume of velocity space at the c vector. So, dx, dy, dz gives the elemental volume in the physical space, dcx, dcy, dcz gives the elemental volume in velocity space, and when we multiply all of them together with the distribution function, we come up with the number of particles located between x and x plus dx, y and y plus dy, z and d plus dz in the velocities which range from differential changes of cx, cy and cz involving the differential amounts of dcx, dcy and dcz. So, you may imagine that the variation ranges over a thin region, which may be indicated schematically using a figure in xyz space or the c space, that means in terms of the location and in terms of the velocity ranges that we are talking about, and therefore, when we multiply the differential changes in the particle locations or the particle velocities together with the distribution function, we end up getting the number of particles per unit volume surrounding that physical location per unit volume of the velocity space. So, with this concept in mind, when the gas is in non-equilibrium, the particles would be distributed non-uniformly in space and time. They will be changing as functions of space and time. Hence, the number of particles confined in the elemental volume in the spatial domain is a function of both the r vector and time. The number of particles contained in the volume defined in the velocity space, incorporating the differential changes of the velocity components, they are functions of time. When the distribution function is integrated over the entire space and velocity ranges that we are talking about, the total particle population of the system would evolve. So, when we are ranging all of them from negative to positive infinity, we are essentially accounting for all particles over all velocity ranges, and therefore, that ultimately gives us the total particle count or the total particle population. Using the distribution function, average value of a physical quantity, any general quantity, please do not mistake this as a partition function. It could be any general physical quantity. We are talking about obtaining an average value, and that may be obtained by using this functional form, where we have the distribution function, the differential changes multiplied with the physical quantity q as a function of space as well as as a function of the r vector as well as the c vector, and then integrated over the entire range and then divided by n, the total number of particles. That is how the averaging comes up when you divide it by n. That gives you the q bar, which is the average value. This has a lot of significance in the kinetic theory world. Let us move on to discuss that since we are dealing with translation of particles in kinetic theory, let us try to see the consequence of assuming translational equilibrium. Just a few minutes back we were saying that in a non-equilibrium situation the distributions are non-uniform. Now, let us talk about translational equilibrium being imposed, and let us see what the consequence is. So, when we impose this constraint, we see constant number density in the entire system, which means n ceases to become a function of r and t. And remember that under non-equilibrium n was a function of r and t. Just to remind you, n is not dependent on location or on time anymore. So, the distribution function essentially simplifies to this the moment its dependence on location goes away. So, from a general distribution function we end up getting a velocity distribution function when the spatial connect is lost. This is a significant simplification. The equilibrium velocity distribution function arises out of that concept, and that is often called as the Maxwellian distribution, which no longer has a connection with the r vector, and it is defined functionally in this form. The above velocity distribution function denotes both magnitude and direction. We will be able to understand the directional issues in a few minutes from now. The above distribution gives the number of particles per unit volume of the velocity space located by the velocity vector C arrow. And when the system is in equilibrium, there is one more significant simplification that takes place, that f is a symmetric function for a system of particles in equilibrium. A symmetric function would mean that starting from f, which is a function of Cx, Cy, Cz, that would be identical to f of minus Cx, Cy, Cz, again equal to f of Cx minus Cy, Cz, or f of Cx, Cy and minus Cz. Now, we are talking about the idea that f also talks about direction. The velocity distribution function talks about magnitude and direction. So, the directionality issue comes in over here. However, when it is a symmetric function, then all these become identical. When it is not, then essentially these functional forms are unequal to each other, and therefore, the directionality will have an impact. This would mean, that means when it is a symmetric function, it would mean that the vectorial implication of the velocity distribution function would lose significance. Only the magnitude of the particle velocity matters now onwards, if we impose the symmetric requirement. So, having said that, this leads to the introduction of speed distribution function. So, we are no longer talking about the velocity distribution, but rather move to a simpler level where we are just talking about speed. And then we define a spherical surface with a radius c, with an elemental sphere above it with an incremental radius of dc. So, the volume of the space between two spheres of the radii can be of radii c and c plus dc can be calculated. It is as simple as 4 pi c square dc, and all particles located on the surface of the sphere of radius c have the same speed. So, let us see the implication of this. Number of particles in the space between the two spheres shown in the above diagram can be represented like this, where you can understand that the central portion basically comes from f c. Now, it is behaving like a symmetric function, and then we have multiplied 4 pi c square dc, that is basically the volume within that annular space, the shell essentially above the sphere of radius c, and the number of particles with speed c per unit velocity change is therefore the speed distribution function x c, which basically comes from this form. You may see that this is nothing but the upper expression without the dc part. Having said that, let us look at how the speed distribution function looks like. If we make a plot, we will see that this is its appearance, and it clearly indicates that not all particles comprising the system are moving with the same speed. Some of them are moving slowly, some of them are moving fast. Those numbers are somewhat lower, while a larger number of particles are in the mid speed range. There are three velocities which are of significant interest. Notice that The one with subscript MP is the most probable, and it has a value of 1 on the x axis, which is given by c divided by under root 2 kt by m. There are another two velocities c bar and under root c square bar. Let us see what they are. So, these are the three important speeds we are talking about. The most probable speed, this speed corresponds to the maximum velocity, or rather the maximum value of the function x, the speed function, which you can of course get by taking a derivative of that function with respect to c and equating that to 0 to find the maximum. The average speed is obtained by substituting q equal to c in the q bar equation, which we have already discussed. It comes out to be under root 8 RT by pi, and then the root mean square speed, which is obtained from the q bar equation again by substituting q equal to c square. The outcome is this. Incidentally, we have already used the c bar equation in many other instances previously. So, we sum up now what we tried covering in this lecture. In this lecture, we discussed about several concepts like sphere of influence, particle, collision frequency, mean free path associated with the translational motion of particles. Subsequently, we discussed about equilibrium velocity distribution, which we are calling as Maxwellian distribution, and the speed distribution function. We also introduced different particle speed estimates, the most probable speed, average speed, and RMS speed. So, with this we come to the end of the discussion on kinetic theory of gases for week 7.